Hello, Chem 2. Hopefully everybody is safe out there and practicing their social distancing. I'm going to give you another video today on the beginning of our next chapter, which is chapter 5. It's all about gas laws. And today, objectives, we're just going to try to be able to, by the end, know what a barometer is, a manometer, and then be able to convert between various pressure units. Little administrative pieces. First, anybody who has not passed the mastery for stoichiometry, there is a mastery makeup exam on the OWL. Right now it's just labeled as stoichiometry mastery makeup. It is worth 72 points. You can take it multiple times until you pass. It's not multiple choice like the other exam, but it does cover all the content in a rather expeditious format. So anyway, that's one option. Second, we are going to have an exam, an assessment associated with aqueous stoichiometry, the unit we just finished up. Right now, that is also on the OWL. You have the ability to take it multiple times, up to 5 attempts, and whatever your best score is what will go into the grade book. We're transitioning into distance learning this week, and you're going to see more and more information coming from your teachers and coming from administration about what we're going to be doing for this stay. And finally, under administrative pieces, there is homework associated with Chapter 5. There's both optional OWL and regular OWL. The OWL that's on there that is required is just simply labeled as required OWL. So go ahead and take care of all that. You're going to be a little bit busy, especially if you're one of the people who still needs to make up that mastery. I have no idea what's happening with times. I'll be in touch as soon as I know more. Okay, so first off, as a warm-up, there's a video that I've linked on OneNote. I'm not going to show it here. This on fun science demos. It's a quick video about what is air pressure, and I encourage you to maybe pause this video now and then go check that one out. It's kind of cool. It's kind of interesting. So I'm going to be quiet for a second for you to pause. Okay, welcome back. We'll see what happens. The video is kind of cool. Hopefully you got a little bit out of it. So this chapter is chapter 5, all about gases and the gas laws. And it's got a lot to it. I'm going to be touching on some concepts from this kinetic theory over and over again. So even though it's listed last, I'm going to mention a lot of the ideas that come up there. But today, the goal is to just get through section 1, talk about measurements on gases, talk about how to deal with pressure and temperature. So section 1, measurements. Okay, so gases. Some issues about gases. One of the things that make gases very, very unique is their physical properties. All gases, regardless of what the material is, as long as it's a gas, they act very, very similarly. They have, no matter what, they have the same amount of pressure. The only thing that is not unique is maybe the density of those gases. Mostly when we're talking about gases, we're talking about very small compounds, mostly non-metallic elements. Sorry, I had to pause there for a second. Composed mainly of non-metallic elements and simple formulas. And they, unlike solids and liquids, they tend to change their shape and change their volume and are able to be compressed. So you're going to see a very, very large difference in the way that these gases act relative to solids and liquids. So things we're going to measure. This unit all revolves around these 4 units of measurement. The volume, that's the amount of space that the gas takes up. The amount, how many molecules are in that space. Temperature, the kinetic energy of the molecules in that space, and then the pressure. And the pressure is a piece we're going to talk about today more than anything else, because I think the other ones are pretty obvious as to what they are. You've probably heard of pressure and understand a little bit about pressure, but what that means on a chemical level and on a physics level is what we're going to talk about today. So anyway, ultimately this unit revolves around these 4. In the past unit, we focused on gases only at STP, standard temperature and pressure. That was 0 degrees Celsius and 1 atmosphere. We're going to talk about in this unit what if they're not. So volume, amount, and temperature, like I said, they all tend to blend together and are pretty obvious. Volume is the amount, the size of the container that the gas can occupy, usually measured in liters, milliliters, or cubic centimeters. Sometimes you'll see meters cubed as opposed to centimeters cubed. And then also, we're going to use the unit of moles to indicate the number of molecules. While I got you here, and it's driving me crazy, my next door neighbor is taking the siding off of his house. So if you hear a lot of banging in the background, that's what that's all about, and I apologize. I want to get this video out to you as quickly as possible. And then finally, jumping over to the other concept, temperature. You guys know temperature of the gas and how that works. It's a measurement of the kinetic energy. And for this one, we're going to only use Kelvin temperature. So whatever the Celsius temperature is, you got a 273.15. If for some reason they give you a Fahrenheit temperature, then you're going to have to convert it to Celsius and then use Kelvin. We only use kelvins. We only use kelvins in the gas law unit. And actually, for most of chemistry, we only use the Kelvin. So what's pressure? Pressure is a force per unit area. You probably heard the term PSI, especially if you're driving now or know anything about cars. You talk about the tires having a pressure of a certain number of PSI. That's pounds per square inch. That's how many pounds are pressing down on every square inch of the container. For the most part, you're thinking about how much the molecules inside are hitting the sides of the container. So in the event of a tire, you're talking about for every square inch inside that tire, there are literally billions upon billions of molecules bouncing off the inside of the tire, generating a pressure, an amount of weight, an amount of force of approximately, in the case of a tire, somewhere around 35 psi, pounds per square inch. The atmospheric pressure is about 14. So right now pressing down on you, and for every 1 square inch of your body is pressing down 14 pounds of pressure. We're a little lower here in Eldersburg, Sykesville, a little bit below at 1 atmospheric pressure. And the thing that is used to measure the pressure is called a barometer. You've probably heard on the weather, they talk about barometric pressure. They talk that the units they use are inches of mercury. But we're going to talk about how a barometer works and what a barometer does to help us out here. So this is what a barometer looks like. A barometer is a tube. It's a glass tube, and it's inverted, and it's a vacuum is drawn. There's no pressure whatsoever in that tube. And what happens is if you put it into a pool of mercury, the mercury, because of the pressure that's pushing down on this area here, the pool will push and force the mercury up the tube, and at atmospheric pressure, at 1 atmosphere of pressure, that mercury will raise to a height of 760 millimeters. Now, why do we use mercury? The biggest reason is that mercury is a liquid, and mercury is very dense. Mercury has a density of approximately 13.6 grams per milliliter, as opposed to water, which has a density of 1 gram per milliliter. So a couple things to realize is they use liquid mercury, first constructed by Evangelista Torricelli. I just know Torricelli. Torricelli is where the torr comes from. You'll see that as a unit in a second. The millimeter mercury is also referred to as the torr because of Torricelli. It's a glass tube inverted in a pool of mercury. The pressure pushes up exactly equal to whatever the pressure is. So if there's less pressure outside the tube, the tower will be smaller. Basically, it's a relative conversion between the pressure outside and the height of the tower. It's a direct correlation. So why we use mercury? Like I said, one of the things to worry about why we use mercury is mercury is very, very dense. If you think in terms of a tower made out of water, if it was 1 atmosphere of pressure outside, if it was mercury, it would raise 760 millimeters or 76 centimeters, a little less than a meter. However, since mercury is so dense, 13.6 relative to 1 for water, if it was water, it would have to be 13 plus times as tall. So that little less than 1 meter height would be almost, I say, over 10 meters tall. That would be really, really tall barometer, so that's why we don't use mercury. It will work. It does work very, very well. However, that would just be ridiculous to use that tall of a tower. So we use mercury. So conversions. These are a list that you need to put into your memory banks. 1 atmosphere is 101.3 kilopascals. A kilopascal is a Newton per meter squared. Is 14.7 pounds per square inch, or PSI is 760 millimeters of mercury, is 760 torr, is 1.013 bars. These are all conversion factors you need to commit to memory. They work as a way to go between one unit to another, from atmospheres to pounds per square inch, from kilopascals to millimeters of mercury. These are the numbers you're going to use, and we're going to talk about that in a second, but these are all the standard temperature pressure. When we're talking in chapter 3 about about STP, we dealt with only the units of 0 Celsius and 1 atmosphere. We're going to convert off of those in this unit. So how do you convert? Well, here's the conversion. Suppose we had 730 millimeters of mercury, and I wanted to convert it into atmospheres or kPa or bars or PSIs. Here's how you do it. So if I have 730 millimeters of mercury, again, each one of these conversion factors represents the same pressure, but in 2 different units. 760 millimeters of mercury is 1 atmosphere. 760 millimeters of mercury is 101.3 kilopascals. 760 millimeters of mercury is 1.013 bar. 760 millimeters of mercury is 14.70 psi. So no matter which conversion factor we use, as long as we're canceling out our units of millimeters of mercury, we'll get a new pressure measurement, a new unit, and the pressure will be measured in that new unit, whether it be in atmospheres, kilopascals, bars, or PSIs. You're just using simple dimensional analysis. You're going to have to, in this unit, very, very often convert to either atmospheres or kPa, kilopascals. In the next section, we'll start introducing what are called the ideal gas laws, and sometimes it's very, very important to actually convert to the same units so we can use the same laws. So atmospheres and kPa and millimeters of mercury are the most common ones used. So besides the barometer, there's one other instrument out there that measures pressure, and it's called a manometer. Now, a manometer is a tube. It's a U-tube, not the U-tube like the video, but the U-tube. There's this J or U-tube here. And what happens is they put mercury in it, and that's what this black liquid, this black material is. It's mercury. And they hook one end up either to the atmosphere, or maybe they'll close it off. I'll show you that in a second. And the other side, they'll hook up to a gas. And what happens is the gas presses down on one side, the atmosphere presses down on the other side, and much like getting on a seesaw with somebody who's much larger than you, if this pressure is greater on the gas side, it will push the mercury up on the other side. And the height, if this material is mercury, the height difference is the difference in the pressures. So if the pressure over here was 760 millimeters of mercury, and say this was a height of 100 millimeters, then the pressure on this side would be 760 plus 100, or 860 millimeters of mercury. So manometer also, it's like I said, it's filled with mercury. The two tubes will have different amounts of pressure. Whichever side is pressure will be pushed down further. So for instance, here is an example of a manometer where the pressure inside here is the same as the pressure outside here, so the heights are the same. And here's a manometer where the pressure inside here is 2 atmospheres, or 2 times 760, and the pressure out here is 1 atmosphere. So it pushes the gas up 760 millimeters of mercury. That is the difference between the two pressures. If it was a vacuum, the way they are the same is if there's no pressure inside here, because there's no pressure pushing down this side. So if there's no pressure pushing down this side, there has to be no pressure pushing down this side, which means they're even. If you had a difference of 760 millimeters, similar to the other one, then the pressure on this side, if this was 0, the pressure on this side would be 1 atmosphere. So here's some examples. It shows you how to do it. If the pressure, think in terms of large kid on a seesaw. In this case, the pressure outside plus the height is the pressure of the gas. This one down here, the pressure outside minus the pressure, the height is the pressure of the gas because the gas has less pressure than the outside. And here they're going to be the same. And the same idea with a pressure of a gas with a closed end. So let's think about this one. So this is something I usually will do in class, so we'll talk our way through it. Find out what the pressure of Px and Py. So Px, the pressure in the first spot, is going to be the difference between the atmospheric pressure. Atmospheric pressure is 730 millimeters of mercury. 730. And then, since this tube goes up, if this out here is 735 millimeters, then inside here, that's less than 735 by a factor of 60, which is the centimeters, or 600 millimeters. So the pressure inside here is going to be 735 minus 600 millimeters, or 135 millimeters of mercury. Then on this side, thinking in terms of what's the pressure over here, the pressure over here is greater than the pressure over here. Pressure in Py is greater than Px by a factor of 300 millimeters. 30 centimeters is 300 millimeters. So if the pressure in X is 135, then the pressure in Y is 135 plus 300, or 435 millimeters of mercury. You can play that back again and have that make sense maybe. So, examples out of your book. They have a couple examples. They have one where they have you do a lot of conversions to try to figure some stuff out. It says that room temperature dry ice becomes a gas, and at 77 degrees Fahrenheit, 13.6 ounces of dry ice are put into a steel tank with a volume of 10.00 feet cubed. The tank's pressure gauge registers 11.2 psi, expresses the volume of the tank in liters, the amount of carbon dioxide in the grams and moles, the temperature in Celsius and Kelvin, and the pressure in bars, millimeters, mercuries, and atmospheres. Wow. Okay, so it wants you to figure out what the volume is, change it into liters, pressure, change it into a couple other units, temperature, change it into a couple different units, and mass, let's change that into moles. Okay, so we got first one, volume in liters. If I know that there's 10 feet cubed and that 28.32 liters is a feet cubed, then the volume of the container is 283.2 liters. This conversion factor is listed in the back of your book. For pressure in atmospheres, I have 11.2 psi at 14.7 psi per atmosphere, or 0.762 atmospheres. For pressure in millimeters of mercury, same thing. I have the psi. I could do this as one step. I could just do 14.7 psi per 760 millimeters of mercury and get that as 579 millimeters of mercury. That could be done just in one step. Also asked the pressure in bars, again, 11.2. 14.7 psi is 1.013 bars. Temperature Celsius, convert that over, you get 77 degrees Celsius is 77 degrees Fahrenheit is 25 degrees Celsius. And of course, Kelvin is going to be 298. And moles, back to stoichiometry. If somebody 13.6 ounces and there's 0.03527 ounces in a gram, again, this conversion factor is found in the back of your book and will be given to you. At 44 grams per mole, I have 8.77 moles. Now, the reason why all these conversions were done is in our next section, section 5.2, there's going to be a lot about conversions, and using the appropriate values in pressure, temperature, moles, and the like. So you're going to do a lot of conversions from a lot of different directions. So as a closure activity, try this. Try this one. Take 0.950 atmospheres and convert it into millimeters, torrs, kPa, and psi. Go ahead and pause the video for a few minutes to go ahead and do that, and then I'll come back with the answers. Okay, so hopefully you tried that on your own. Your answers are, there's 722 millimeters of mercury, 722 torr, 96.2 kilopascals, and 14.0 psi. Hopefully you did that correctly. So what's next? Our next video, which will be later on this week, will be the start of the gas laws. And there's a lot to this, but it's actually just a whole bunch of gas laws, a whole bunch of ways to interrelate pressure, temperature, volume, and number of molecules and how they relate together. And we'll do that with our next video. Reminder, if you need to take the mastery, go ahead and take care of that online. Please go ahead and do the aqueous stoichiometry exam when you can. Sooner the better, so it stays fresh in your mind. And then you still have the homework for the other two. I'll see you next week, and hopefully I'll see you before too long, and this craziness of the virus and the distance learning is put aside as quickly as possible. Anyway, stay safe, wash your hands, practice social distancing, and always remember and never forget, sig figs do matter. Bye.